because it's 20
good
past.
idea. Good idea.
Okay, cool. So, hi, my name is Lisa Szalagina. I'm from London. I will be chairing the session, Argumentation III. And the first talk is given, it's going to be, well, online, given by Samisa and João Alcântara from the Federal University of Ceará in Brazil. So, Sami, if you could share your screen and start. Because right now we're still seeing Nico on full screen. Cool, great. Sami, you are muted.
Okay, there we go.
Great, yes.
All right, so you can see me and you can hear me, right?
Yes.
Can you all hear me?
Yes.
Yeah.
So, okay, then I'll start. First of all, good afternoon to everyone, especially those on site. And this presentation is a little bit tricky to do in just 15 minutes because the paper itself is quite dense. There's a lot to cover here. And I'll do my best to cover everything with just figures and examples. This joint work with João Alcântara, who is my PhD advisor, and we both work at the Federal University in Brazil at Ceará. The goal of this paper is to give a new take on how argumentation frameworks and abstract argumentation and logic programs are related semantically, and we revisit the problems to cover a few issues using a new take on argument labelings, using 5 values instead of 3. So I'll be mainly covering what we do and why it was necessary. The key things here are on semantics that minimize undecidability in each of the systems. So overall, this work builds on previous papers, mostly works by Martin Caminada, some of which we participated in. And these are only a few of the papers. We also did comparisons between logic programming and CETAF and ABFs, ABA. We covered a lot of stuff and maybe almost a dozen papers, I think. And overall, what we do is to compare the expressiveness of the systems to make sure if they are really different or not, why they are different, is the different actually meaningful, if anything. And in each case, it revolves around finding translations from the theories from one system to the other. I'll just call them theories and models because they get different names in each case, right? In abstract argumentation, we're talking of frameworks. In logic programming, we're talking of programs, and we talk of atoms. The other talk about arguments. So the names change, but fundamentally what we have are theories, and we need to translate from the theories of one system to the other in order to map the semantics they have and the models that will appear in each semantics, right? In abstract argumentation, we get extensions or labelings. In logic programming, we actually call them models. But these things are related. They have the same root on non-monotonic reasoning coming all the way from circumscription. And for this reason, we can, it gets tricky to do those comparisons because we need to map syntactic artifacts, which are the theories, the sentences, wherever they are called, and use them to compare the semantics. So all the time we're looking at the same time at syntax and semantics, and we're using translations and functions to map one thing to the other at both levels, syntactic and semantic. And this work in particular is on abstract augmentation logic programming. So if we look at that particular setting, what we find is that in abstract augmentation, we have, when we use augment labelings, we have three values, three truth values, which are usually said to be in, out, and undecided. Right now, an argument can be accepted, rejected, or left undecided, but usually use those values in, out, and deck. And in logic programming, we just talk about true, false, and undecided. The core semantics, which are usually used here, they're based on some kind of semantic equilibrium between the three values. Or the complete semantics in abstract augmentation, and the three-valued stable semantics in logic programming. And the other semantics, the other mainstream semantics in each case here, they can be obtained from those core semantics by just manipulating and checking the sets of accepted, rejected, or undecided arguments or atoms in each case. And what we find is that the same operations, starting from the core semantics, once we compute them, the same operations in general will yield, will retain the correspondence in the two systems, except when we come to the semi-stable and L-stable semantics, which are the two semantics where we try to minimize undecidedness. And this is a little surprising. It only happens really when we try to translate from logic programs to abstract augmentation, not the other way around. From abstract augmentation to logic programming, it's very straightforward. The translation is immediate and the results hold completely. They will actually coincide. They don't even need a mapping in the semantics. But when we try to go from logic programming to abstract augmentation, we find some obstacles. And overall, the intuition here is that there are several intuitions really, but the main one is that the interpretation of undecided changes in each of the systems, even though the corresponding interpretations of true and false are basically the same. We studied a lot this problem, and I'll be trying to cover here what we do and how we do it. But really, to get there, I need to show you why the difference happens. So I'll mainly focus on that, and then I'll just comment on the results that follow. So concerning why they are different, we managed to find that sometimes that there are only some arguments that are responsible for the differences. And before I proceed, I just want to show, in case there's anyone who isn't familiar with abstract augmentation frameworks, what they are. And they are just a set, it's a set of arguments and a binary relation, which is interpreted as a attack relation between them. And when we have an attack such as this one, like A1, A2, this means that A1 attacks A2. And fundamentally, it means that A2 can only be accepted, it can only be deemed as true if A1 is not. The attacks, an argument can self-attack and so on. And the semantics are given by labelings attributing those three values, in, out, and undecided into them. I am printing green for in arguments, red for out arguments, and blue for undecided arguments. This framework, for the first example, has those three argument labelings. There's a possibility where A1 is accepted, and that chains up on the rest of the framework. There is the possibility that A2 is accepted instead, and it also has consequences and so on. Each evaluation gives consequences to the other arguments. So this other example is a bit more informative for what we need. It's just slightly more complex, but what I want to show you here, it also has three argument labelings. And what I want to show here for you is that argument A4 is always undecided, while argument A3 changes a little bit, right? And in the second labeling, it can be out, can be rejected. But the thing here that's one of the obstacles we found is that there's no way to know in abstract augmentation using this kind of translation that we originally had from logic programs to abstract augmentation frameworks. There is no way to tell whether A3 and A4 have or not the same conclusions. They could have the same conclusions, given that they would be instantiated from some knowledge base, and they could have different conclusions. There's just no way to tell that. But the problem really appears on this kind of, in these comparisons, when we want to draw some conclusions from the abstract argumentation framework. The general process is that we have a knowledge base, we instantiate arguments from it to get an argumentation-based, an argumentation framework. We take the semantics from the framework and as argumentation semantics, and then we map that to an evaluation of the conclusions of the arguments. And then we have models from the original knowledge base. That's what is expected overall when we work with instantiated argumentation. And here we will have some problems, because if we consider possible conclusions for those arguments, and especially when we consider the scenario where A3 and A4 have the same conclusion, there will be a difference in mapping here, right? There will be a difference in mapping from the arguments to the conclusions. Here we have that if we try to minimize on the sidedness on the argument level, only the second labeling will satisfy that. It will be the labeling where the undecided set of arguments is minimal. When we look at conclusions, you see that there are two corresponding labelings, conclusion labelings that would be obtained from those argument labelings, where the set of undecided conclusions are both minimal, which should be C1 and C2. So there is a mismatch, right? And fundamentally, in this example, this is the simplest example I could build. The problem here is that A3 is actually irrelevant to the evaluation of the other arguments, of all other arguments. For instance, it only attacks itself in A4. It doesn't matter that it attacks itself, because what really determines its evaluation is A2 in the end. And it doesn't change at all the evaluation of A4. So A3 is fundamentally relevant to the evaluation of the other arguments. It doesn't affect any of the other arguments. And we started looking at how to identify those arguments that are somehow irrelevant. That's what this paper is about. There are mainly two situations, and I'll only cover one of them because of time and to try to keep things simple. But those are the main obstacles in abstract argumentation, especially when we pick the main way aspect and aspect plus will instantiate argumentation frameworks for a knowledge base. We can have multiple arguments for the same conclusion, and usually there's no way to tell whether or not those arguments have or not the same conclusion at the abstract argumentation level. So our solution goes in two parts. The first part is to include a set of new arguments we call default arguments, which fundamentally will do that. They will help us group the arguments that have the same conclusions. And based on that, based on the addition of default arguments, we adapt the argument labelings to differentiate between those arguments that are relevant and those that are not. So the default arguments are very straightforward. We don't really need to look into how the argumentation framework would be instantiated from knowledge base. We only need to know, we only need to assume that the original framework I showed here was obtained from some knowledge base. And now we can look just at the difference. So the thing here, the default arguments, they correspond to the negation of possible conclusions the arguments have in the framework, one for each possible conclusion. So in the end, they do not attack any arguments, and every argument that has the same conclusion will attack the same default argument, because each argument only attacks, each non-default argument will only attack a single default argument. Effectively, this allows us to tell that A3 and A4 have the same conclusions, assuming the conclusions we had before. And now we have a bit of a difference. We can see better that A3 is irrelevant because the default argument A3 is always undecided. right? So it's only really affected by A4. A3 is fundamentally irrelevant here. And also the evaluations of the full arguments, they will mirror the evaluations of the conclusions. So at this point already, we have a good part of the solution. Now, to actually differentiate those two semantics, what we have to get is that we have to change a little bit the argument labeling. And the way we do it is that we can have two scenarios. In one of them, we have an argument that's labeled out, that is not relevant, which is what happens in our example. And the other scenario is that we have an argument where it's undecided and it's actually irrelevant. It could just as well be out. So to figure that, we specialized the undecided label in two new labelings, which we call I don't know and I don't care. I don't know is just an undecided argument that really should be undecided. And I don't care is an undecided argument that could just as well be out. And we do the same for out. We just call it out if it should be out. And we call it, it doesn't matter if it's out, if it could be undecided without consequence. So the difference is that in the second labeling, A3 would, instead of out, would be labeled IDO. It doesn't matter if it's out. And from there, we can get to a conclusion that really in the conclusion labelings, what we are really minimizing are the conclusions of arguments that I don't know with I doubt. It doesn't matter if it's out. So to jump here, this is the main result we have concerning semi-stable and L-stable. The L-stable semantics from logic programming would be given by what we'd call semi-stable conclusion labelings. And at the argument level, semi-stable semantics minimizes I don't know if I don't care, while at the conclusion level, it minimizes I don't know if it doesn't matter if it's out. That's where the difference appears, and that's why our specialization of the labelings will help pinpoint this, right? From there, we could propose a new semantics for abstract augmentation, which is also based on minimizing undecidedness, but it is the one that will minimize I don't know, and it doesn't matter if it's out at the argument level. It's just slightly different from semi-stable. It has basically the same properties. And we think about writing another paper just to explore those, to actually present this semantics, because here it is
I'm sorry,
kind of a corollary.
I will interrupt you because we only have 3 minutes for questions left.
Yeah, I was just ending. That was it.
Cool. Thank you.
Thank you.
Any questions from the audience? Okay, are there any questions from the online people?
There's a question. I don't know if you see it.
May I ask?
On the chat.
Raising my hand. May I ask? Can you hear me?
Yeah, of course.
Okay, great. Thanks for this presentation. Do you have any thoughts on argumentation semantics that are not admissible set-based? So the new semantics family of weak admissible set-based semantics that now is creating a lot of buzz, or that is much appreciated by the community, or naive set-based semantics like CF2 and stage 2 semantics.
Well, I come from a background of logic originally, especially on logic programming. And I tend to think of everything in knowledge representation in terms really of theories and models and so on. And all I have to do about this is that when we come to the point where we are instantiating arguments from a knowledge base to try to reason with this knowledge at the level of arguments, we need admissibility. That's all I can say about it. The other ones, not admissible, even weak admissible semantics, they will tend to generate inconsistent results concerning the underlying logics.
So, okay, so, thank you. So it would of course be great to have a rebuttal of somebody who I don't know, I guess there's a motivation, right? I guess somebody who designs weak admissible set-based semantics might say something different. But it's an interesting point for sure. Thanks.
Thank you for your question.
Okay, great.
Then we will move on to the next presenter, who's going to be Nico Patika from the University of Stuttgart. So, Sammy, if you could stop sharing your screen, and then Nico will share his screen.
Before I do that, let me just say that I couldn't identify the author of the question. So maybe if you could email me, we can discuss some more about it. Thank you very much.
Okay. I hope you can see my screen.
Yes, great.
Perfect. Okay, so I will talk about generalizing complete semantics to bipolar argumentation frameworks. And I will start with the basics, and I will also tell a little bit about the things that Henry mentioned this morning in 3 slides. So the setting is again abstract argumentation. So what we consider here are basically argumentation graphs where the nodes are arguments that can be accepted or rejected, and the edges in the basic case just correspond to attack relations. And then the computational problem is basically to decide which arguments can be accepted. So then this question can be answered in different ways, and this basically leads to different semantics. And semantics, again, can be defined in different ways, but what we will focus on here are labelings. So labelings assign a label to every argument. An argument can be labeled in, then it's accepted. It can be labeled out, then it's rejected, or it can be undecided. So Sammy also mentioned this before, but I will just repeat it quickly. So then one very fundamental semantics is the complete semantics, and this is basically defined by 2 conditions. So we say that the labeling is complete if 2 conditions are satisfied, and the first one says an argument is labeled in if and only if all attackers are out. So this argument here does not have any attackers, so it must be labeled in by the first condition. And the second condition says an argument is labeled out if and only if some attacker is in. So this one is in and it attacks this argument, so this one must be labeled out. And then by the first condition, these 2 arguments are only attacked by this argument that is labeled out, and so they must be labeled in again. So then Henry mentioned this morning that it makes sense to talk about the application context. And the application context that I am thinking of here is what Tony called aggregation of perspectives. And this, for example, happens in review aggregation, for example, in the context of recommender systems or something like that. So in the terminology of Henry, I think the arguments would be considered as statements. So for example, if we think about a product, then there could be statements like the product functions well, product feels poorly built, the product is affordable. And some of these statements speak for and others speak against the product. So often these arguments are extracted from natural language, and so there's usual uncertainty about these arguments. And the question is, how can we represent this? And in recent years, people also considered this in lots of other contexts. Francesca Toni's work, for example, considered lots of applications also in review aggregation. But what Tony in particular considered was the one probabilistic approach to argumentation. This is called the Constellations Approach. And the idea here is that you consider a probability distribution over argumentation graphs. And in our example here, perhaps we have these 4 argumentation graphs that we think may be the right ones, and then we just consider a probability distribution among them. And then we could assign a probability to every argument, where the probability can be understood as a degree of belief by just looking at every argumentation graph, see if it accepts the argument in a particular way, and then just adding up the probabilities. But I think the problem with classical argumentation frameworks where we have only attack relations is that in review aggregation, we usually do not only consider contra-arguments, but we also consider pro-arguments. So it seems to me that at least in this context, we need more. And what we need are basically support edges that we, for example, have in bipolar argumentation. So in bipolar argumentation, we just add a second type of edges denoted by these dashed edges here, and these are then support relations. And then the question is again, which arguments can be accepted? And again, we can define this in many different ways. And I will just give one example. One of the first semantics, I think, was deductive support. And the idea here was to translate the bipolar argumentation framework to a classical Dung framework where we have only attack relations. And in order to do this, basically two meta attacks were introduced. So we say that there is a supported attack from an argument A to an argument B if A directly or indirectly supports an attacker of B. So then we say there's a supported attack from A to B. And the second notion is the mediated attack. We say there's a mediated attack from A to B if A attacks an argument that is directly or indirectly supported by B. And then in order to define the semantics, what happens is basically that we add one attack edge for every supported and mediated attack, and then we delete the support edges. So just to illustrate this, let's consider this example here. Then we have a mediated attack from this argument to this argument, because it attacks an argument that is supported by this argument. So we would add this mediated attack edge, and then we would delete the support edge. And then, for example, when we would consider complete labelings, we would basically get this labeling where this argument must be accepted and these two must be rejected. But if you think about the original framework, it's a little bit weird because the attacker and the supporter are in the exact same position. And for some reason, favor is given to the attacker. And in some applications, for example, in review aggregation, I think this is not particularly reasonable. So what we would need is basically a semantics that treats attacks and support equally in a sense. There are some earlier proposals. So there are lots of proposals. I will just mention a few. So there's this notion of deductive support. And then another semantics is the deductive semantics that respects these special attack relations that you can derive from support relations in deductive support. But the semantics is rather indecisive. So we have lots of labelings and lots of arguments are labeled undecided by these labelings. So it's not particularly nice. So then some other refinements exist that only weakly respect this deductive support. And as it turned out, they generalize stable semantics, which is actually a refinement of complete semantics. So a stable labeling is basically a complete labeling that does not label anything undecided. So given that there is this relationship, these particular labelings generalize stable labelings, one may ask, is there a generalization of complete labelings to bipolar semantics? And if we had something like that, then we could just consider the same refinements as before and would get something like stable semantics and all these other refinements like semi-stable, bounded, and preferred labelings for free. So that's basically the idea here. And this generalization that is introduced here is by complete semantics. And the main questions here are basically the following. So the first question is, can we generalize complete semantics to bipolar graphs similar to these generalizations of stable semantics? And then is the generalization more expressive? So if you look at deductive support, then everything is basically translated to an attack-only framework. And then support edges actually do not add any expressiveness. So the question is, does this actually add expressiveness? And if not, there's probably no point in considering bipolar argumentation, because we could express the same things with attack-only frameworks. And then the final question is perhaps how are the refinements of these bicomplete semantics related to refinements of complete semantics like grounded, preferred, semi-stable, and stable. So in order to define this bicomplete semantics, we consider a notion of domination, and domination is defined as follows. So we say that the attackers of an argument dominate its supporters if the following is true. We say this is so if the number of attackers that are labeled in is larger than the number of supporters that are not labeled out. So this includes supporters that are labeled in, but also supporters that are labeled undecided. And intuitively, for every one of these arguments, there must be an argument that is labeled in, and there must be an additional argument. And then we consider something symmetrical for supporters. We say that the supporters dominate the attackers if the number of supporters that are in is larger than the numbers of attackers that are not out. And then in order to generalize complete semantics to bipolar graphs, we basically take the two conditions that we have for complete semantics and we extend them to bipolar frameworks. So the first one says an argument is in if and only if all attackers are out. And now in the bipolar setting, we say an argument is in if and only if all attackers are out as before, or we allow an additional case here. This is also the case if the supporters dominate the attackers. So supporters do not exist in this setting. So this condition here can never be satisfied in the attack-only setting. And so in this setting, they would actually be equivalent. And then for the second condition, which in the original setting says out if and only if some attackers in, we say out if and only if the attackers dominate the supporters. And again, supporters do not exist in this attack-only setting, so these conditions are again equivalent. If there's an attacker in, then they immediately dominate the supporters because there are no supporters at all. So if we look at the initial example, again, of course, this is a very simple example, but just to illustrate the intuition, then what happens is basically these two arguments here are not attacked, so they must be accepted. And then for this argument, we basically cannot make a decision because there is an attacker and a supporter. So we basically have to label it as undecided under the semantics. So in order to make a decision, we would have to collect more evidence. Basically, we could have an additional attacker and then the argument would be labeled out, or we could have an additional supporter and then the argument would be labeled in. So then the first question was, can we generalize complete semantics to bipolar frameworks? And this is actually the case for the reasons that I explained before. So it basically follows from the definition. So this bicomplete semantics actually generalizes to complete semantics in the sense that when you consider a bipolar framework without supports, then the bicomplete labelings are exactly the complete labelings for the corresponding attack-only framework. But then I mentioned we are also interested in something that is more expressive. So the question is, of course, how we define more expressive. And here's one suggestion that makes sense in this setting, I think. So we say that the bipolar semantics S prime is more expressive than an attack-only semantics S, if and only if there exists a bipolar argumentation framework such that there does not exist a DOM framework basically that has the same labeling. So in other words, for all DOM frameworks where we consider arbitrary attack relations between the arguments, the labelings are different from the arguments, from the labelings for this bipolar argumentation framework. Okay, and then we can show if we have any DOM semantics that satisfies two simple conditions that I call isolated acceptance and hard attack, then the bi-complete semantics is actually more expressive. So isolated acceptance is a very weak condition. It says an argument must be labeled in whenever it does not have any attackers, and hard attack says an argument must be labeled out whenever an attacker is in. And then the bi-complete semantics is more expressive, and these conditions are met for the complete semantics and all refinements basically. So I will skip some things because I'm already out of time, I think. But in the end, we can then say the bi-complete semantics is in a sense strictly more expressive than the complete semantics. So strictly more expressive here means that it's at least as expressive in the sense that it generalizes the semantics, and it's also more expressive in this other sense that I mentioned before. And then you could also relate it to the grounded, preferred, semi-stable, and stable semantics. It does not generalize these semantics, but it's still more expressive. Okay, and I will skip the other results because I'm out of time. And just to conclude quickly, so what was introduced in this paper is basically this bi-complete semantics that generalizes complete semantics. And as opposed to deductive semantics, supports do actually add expressive power, and the power of attack and support is balanced. So we do not have this imbalance that we saw before for deductive supports. So then these definitions of generalization and more expressive can perhaps be improved. So I'm happy to discuss this. And one potential disadvantage compared to other approaches is perhaps that in this setting, you may want that supported supporters are stronger than unsupported attackers, or supported attackers are stronger than unsupported supporters. But this is actually not the case here. So this is perhaps something that one could try to improve. And that's everything I wanted to say, and so I will stop here. Thank you.
Yeah, okay.
With the online people, so yeah. Yeah, Nikki, who's raising their hand?
Yes, thank you very much for your interesting talk. If I understood you correctly, then the support and attack relations are qualitative in your approach. Do you also consider to investigate weighted attacks or degrees of support or something like that?
Yeah. So there are approaches that do that. So, for example, there are these rated or gradual bipolar argumentation frameworks that do that. But this goes in a different direction. So I did something like that, and many other people did something like that. But in this context, I was really interested in these qualitative frameworks because they can be extended to quantitative frameworks by this idea of this Constellations approach, where you basically take lots of quantitative frameworks and then you consider a probability distribution over these qualitative frameworks. So now we have our qualitative bipolar argumentation graphs. We consider a probability distribution over them. And in this way, we can actually represent uncertainty. Perhaps not the uncertainty that you have in mind, but uncertainty about, say, the existence of arguments or the existence of attack relations or support relations. And I think this is useful in the context of argument mining, where you try to extract arguments from text. And then there's some uncertainty about if something is really an argument and if it's a supporter or an attacker. I hope that answers the question.
Thank you, yes.
Are there any
Questions from the audience? No?
May I ask a question, Nico?
Of course, I'm happy about questions, but Lisa has to look at the time zone.
Okay, my question is it possible to generalize other semantics like a preferred or stable semantics to bipolar argumentation frameworks, or you already done this in this paper or not?
Yes and no. So since I generalize complete semantics, you get generalizations. So there was a caveat. So it definitely works for semi-stable and stable semantics in a straightforward way, but there may have been problems for grounded and preferred semantics. So what you can definitely do is you just take these bi-complete labelings, and then in the same way how you define complete labelings, you define bi-grounded, bi-preferred, and so on. So grounded is usually defined by minimizing the in labels, preferred is defined by maximizing the in labels, and so on. And when you do this, you get these different notions. And for these two, it's actually the case that they are strictly more expressive. So they generalize semi-stable and stable labelings, and they are also more expressive. And I think these two should also generalize grounded and preferred, but I'm not sure. So I think there was something weird about the semantics actually, and this is why I didn't consider them, but I do not remember exactly. So it's a very good question. I have to check again, then I come back to you, send you an email. I don't know from the top of my head. For semi-stable and stable, it works in a straightforward way. For these two, I'm not so sure.
Okay, thank you. Maybe I definitely will read your paper later when it published. Thank you.
Okay, thank you, Nico. Our final talk for today's session is presented by Serjan Vesic from the University of Artois, and his colleague who's not here, Bruno Jung from the University of Aberdeen.
Okay, so thanks for the introduction. Thanks everybody for coming. My name is Serjan, so I'm a researcher at CNRS, French National Center for Scientific Research, and affiliated with CREER Lab in the north of the country, joint work with Bruno, and it's his birthday today, so happy birthday, Bruno, if you're watching, and hello to thousands and millions watching the live YouTube stream. Okay, back to so we are going to talk about argumentation, thanks. And I hope you are familiar with the framework, else I'm gonna do an extremely brief crash course. So this is how we do it. We have graphs, and so those nodes are arguments. So in this example, we are talking about whether to go jogging, and this is attacked by two different things. One is that the weather is too hot, and another is that it's raining. So different people introduced different frameworks. Some of them introduced also the weights. So the motivation here is, if you put the weight on an argument, so there are different motivations, and one of them is that if it's 28 degrees, you can put 0.6, but if it's 32 degrees, then you can put 0.7 or 0.8, depending on where do you live, so how used to heat you are. And same for the importance of jogging as exercise. Also, there are people who studied weights on attacks. So this means that you can model the fact that for some agent, this attack is not so strong. So the agent also has a temperature, and they also agree it's 32 degrees, but it's not such an important reason for cancelling or postponing the jogging. And similarly for the rain. So then some other people, or some of those also defined the semantics that given this type of information can attach a degree to each argument. So without further continuing this, let me also thank Henry for the inspiration for this example, because it's from his paper. But of course, this goes without saying that he's not responsible for any of the claims I state here. So you've seen this example on the left, just checking if it's not on the mirror. Now, in the middle, so the motivation is also from the literature. Also, Nico cited some of the works from K. Roll, from Van der Tore, from different authors, also Serena Villata, etc. And there are different types of support. So there is also a big debate here. So some of them justify this as telling that for, you can imagine a guy or a girl who says, actually, if I'm a bit wet and then it's hot, it's not such a big deal. So it's actually those two together are going to improve the acceptability of the jogging, because it's easier to run if we are a bit wet. And then you have the third example, which is the contrary, somebody who says hot, humid weather it's just a catastrophe, it's the worst thing that can happen, my heart is going to stop, I'm not going to jog. So they're going to add even more attacks. So as you see, this joint attack, and so those are different things that some people introduce over the course of the years. And this is how we obtain this bipolar, because we have both attacks and supports, and SETAF, because AF stands for Argumentation Framework, and then SETAF stands for Argumentation Frameworks with sets of attacks. And so we studied this framework a bit with Bruno, and we studied different frameworks which are strictly less general, so frameworks where you have bipolarity but not set attacks, and then frameworks where you have set attacks but you don't have bipolarity, etc. And there is a lot of things happening there, so we try to make a systematic view of this and to see if we can have a unified framework and what would happen with the existing principles, existing semantics, and so on. So it's not really to introduce completely new principles, it's more to study what people introduced and to see if it can be slightly generalized to fit into this framework, and then see the links, etc. So I'm going to give you a bit more information in the next 5 minutes. So this is the formal definition. I already mentioned this on the example. So you have arguments, this, then you have attacks and supports that can be also, that can come from the sets. And you also have those weights. So this is just a formalization of you have seen. And here also I'm just stating the 3 classes. So this is also not from ourselves. We don't have a specific motivation, except that people define them. So we wanted to compare what happens. So the first is just the class of all frameworks you can imagine. The second one is in some of the semantics, some of the papers, people claim that if I'm not mistaken, I think in work of Leila and Jonathan Benaim, that you can, any argument cannot have the initial weight 1 because nothing is perfect, something like this, so that has this class. And then there is the third class also where nothing can have a value 0, with some of the possible justification. If this argument has the value 0, just don't include it in your framework, etc. So with Bruno, we took a kind of a mathematical standpoint, so we didn't really judge them and just try to compare them and see what happens. So why people study those principles at the first place? So principles exist in many disciplines outside of argumentation. You all know about social choice, about impossibility theorems in different types of logics, etc. Probabilistic model logics, and they help us to understand the systems. So we try to generalize and see what happens in those frameworks I mentioned. So I'm going to try to make, what was the word? Procatalypsis now. And so if you read the thesis of Jérôme de Lobel, or if you attended the talk of Henry, you know what it is. So it's when you attack yourself and then you defend yourself. So it's supposed to be, supposed to help you convince the audience. So if I attack myself and say that, of course, you cannot impose principles on the abstract level, which is, of course, a reasonable argument. And then let me answer to this a bit. So we don't really impose. So first we took those principles, and then also we are not claiming any of those are mandatory. So we don't say that you need to satisfy equivalence, etc., because it would be really too much, because we took different principles from different papers and different frameworks, and we are not aiming at a particular application. So we don't claim you should satisfy. Also, the union of all the principles is not even consistent. So even if you want, you cannot satisfy all of them. So this is just kind of an overview, and we try to compare and see, and if at some point you want to apply some of those semantics, you will know what principles are going to be satisfied. So some other benefits of the principle-based approach are listed on the slides, and you can guess in some other areas also how it works. I'm not gonna spend more time explaining this. Let me show you some of the principles that exist. So I took some of the simplest, so it can fit on the slide, and you can get an idea. So if you're interested, of course, we can discuss during the break or on this 3D spatial chat. So stability says that if an argument is not attacked or supported, then its final overall, what people call overall acceptability degree or final strength, should be the same as the initial one. Equivalence is a bit more interesting and also a bit more controversial, because it says if you have different arguments and they might have different attackers, then their acceptability degrees depend only on the strengths of the attackers, but not on their grandparents and the others. So this was accepted like maybe too fast, and so basically all the semantics satisfy this, but then we recently challenged this a bit, discussing a paper, and also proposed some semantics that don't satisfy it. So it's going to be presented in CLAR very soon. And so let me show you more principles. I'm going to speed up a bit. So directionality, for example, says that if you have those two graphs, so the only difference being one more attack, that, for example, the accessibility of A or E is going to be the same on the left and on the right, because this attack is just going to influence C and D, and so on. The monotonicity says that, here I'm just going to skip the theory and just show you the example. So it says that basically you have the same attackers and the same supporters. So if you have some more supporters, so A has more supporters, then it claims that A is going to be stronger or equal. And then we were especially, we spent a lot of time looking at the links and the incompatibility. This was the interesting part. And also we had to dig into some definitions and proofs from the more particular cases. Then we also found some errors in some papers, also some proofs, so it was fun. And so I'm not going to read everything, but basically we say if you satisfy this, then you must satisfy also some other principles. So this is interesting to study. So we have some results of this type. And then we also tried to we took some semantics like Euler base from Amgud and Benaim. We also took DF quad from Antonio Rago and colleagues, and we took sigmoid damped semantics from Mosakovsky and Neuhaus. So we generalized them to our framework because they were not general enough. and then we try to see what happens. So also we fill in the satisfaction table. So on the left are the principles, and on the upper side those three classes people studied, and also the principles. So we try to compare them like this. We also feel there are some principles probably missing if you want to characterize them mathematically, to have some characterizations. But I'm not going to talk more about this, to try to stay in the time limits. We can discuss it later. So we studied the existing principles and existing semantics, tried to generalize them, to put them in the same framework, and studied the links between the properties and the satisfaction of those principles. That's all from me. Thank you.
Okay. Yeah. Cool. Then let's start again from here. Yeah, Nico, if you want to ask your question.
Sure. So I think this is very interesting. I think sets of attacks and sets of supports are very useful. So do you only consider sets of attacks or also supports?
Yeah, you have both.
So we put everything. So maybe it's probably too much for a real application. It was, I must admit, more of a mathematical exercise to put everything in the same, so we could compare. So you can weights on attacks, weights on supports, weights on argument attacks and supports, and set attacks and set supports.
Yeah. So what is the general idea? How do you combine sets? I mean, instead of having one argument that supports or attacks something, now you have a set of arguments, right? What's the main difference in the definition?
Yeah, so no, it's just a definition. You allow for this, so people can define and say A and C together attack B. So they just attack it together. So so what is the exact question? You allow.
So I'm wondering.
I mean, when you look at the definition, you somehow, what happens is usually you aggregate the strength of attackers and supporters, and then you somehow adapt the initial weight, right? And
usually when you aggregate the strength of attackers and supporters, for example, you do something like in Euler-based semantics, for example, you add up the strength of supporters and then subtract the strength of attackers.
Yes.
And I wonder, how do you define this here? So instead of summing over the single arguments, you perhaps...
yes. I see the question. So here you can have different aggregation functions. So you can, are you talking about how to aggregate the weights of the arguments?
Yeah, exactly.
Yeah, so you have different aggregation functions, and the simplest is, of course, one of the simplest is to do like a weakest link. So you could go with the minimum, but you could imagine the others also. Yes, they would also be highly dependent on the application, of course, and the instantiation. So yes, a very good question. How you could do all of this? Yes.
Oh, thanks. I will read the paper.
I can show you later.
More of the technical details, maybe we can have.
Yeah, let's use the spatial chat. Thank you.
Yes, thanks.
We still have 4 minutes of time. So John was very efficient and fast. So if there are any more questions, there's another one. Yeah. Samuel.
Yeah. Hi, I have a question. So, your graduate semantic, can you graduate semantic cover other graduate semantics, like Sandra McGill's graduate semantics and other semantics?
I didn't get it.
Can we cover which one?
I mean, you proposed graduate semantics, right? And there are other graduate semantics, like Sandra McGill also proposed some semantics. So your semantics cover their approach?
I would have, yes, I see. Do you refer to the work with Sanjay and Davide? Yeah, yes. Okay. So we would have to check if the framework they use is the same. So if they have the same thing at the input, and if they have the same thing, so at the output, those semantics we studied, they produce, they attach a number between 0 and 1 to each argument. So if that is the case, then we could study it in this framework. If they produce the extensions, then we cannot.
Okay. Okay, thank you.
Okay, thanks. So I have to check this. I think they produce the extensions, right?
Yeah.
Yeah, so we cannot study it in this framework. This is made more for the gradual output.
Okay, thank you.
Thanks.
Is there anybody from the on-site listeners who has a question? Okay, now then Nico, then did you have another one?
Sorry if there's still time, otherwise I will just ask later.
Okay.
But before you said there's still 4 minutes, so...
No, well, there's still 2 minutes.
Okay. So quick question. So there was this idea by Lina and one of her PhD students to consider something like a similarity function or something in between.
Yes.
And this framework of Mossorkowski and Neuhaus, you have this aggregation function followed by the influence function. And they just put in this other similarity function, and then instead of 2 functions, you have 3 functions. I wonder if you can unify what she did and what you did by just generalizing this third function, because the third function probably just summarizes somehow arguments, right?
Ah, okay. So you want to include the measure of similarity of the arguments, and it's going to impact the strength of attacks and supports?
Yeah, something like that maybe doesn't work. I just thought in your case you also have a function that aggregates somehow, in your case sets of attacks instead of similar attacks. Yes. And I was thinking that perhaps you can unify the 2.
Oh, okay. Thanks for the question. So yeah, I don't know. I will have to dig in the detail. Yeah, I will have to dig in into the details of Leila's definition. And then to see if it, I think it's compatible, yeah. I think it can, but it's gonna be really, it's already a bit too complicated, so it's gonna be really but maybe it's possible, maybe something interesting, maybe we are gonna ask ourselves some interesting questions if we try to do it. Okay, thanks, yeah. I'm gonna keep you updated when I try it.
Okay, cool.
Thank you.
That concludes the talk, thank you.